So next we have Mousumi Das telling us radio X-ray study of hard and warm gas around isolated galaxies in voids.
Okay, good afternoon. I also want to thank the organizers for giving me the opportunity to speak here. I'm going to speak about places where there's hardly any matter, and most of this meeting and all meetings is about matter, but I'm going to talk about galaxies which are residing in the most loneliest part of our universe, within voids. And this work is a collaboration with many people, notably the last person, Tuhin Ghosh, he gave a talk on the first day, and he's gone now, but I'll present some of the work again that we have been doing together, and this is his student. Okay, this is a very quick outline of my talk, because I know that void galaxies is not a commonly heard topic, so I just want to give a short introduction about those galaxies, and then talk about our studies of the diffuse emission detected in voids. Now, voids, as we all know, are the emptiest parts of our universe, and matter flows from low density regions to the walls and filaments in voids. So you have, as the universe evolves, you have more and more matter emptying out of voids. And so you have clusters like this, and you have voids, empty regions like this. Now, one thing I want you to notice is that within the void regions, there are also these filaments. And these filaments come because within voids, there is a hierarchy of structure, subvoids you could say. And as the universe evolves, these subvoids, empty regions, merge. And when they merge, we often end up with small filaments of galaxies. And that is very clearly seen in the observations of nearby voids. So this is, I just wanted to show you to demonstrate that the voids are emptying and emptying more and more of mass. The volume remains the same. But in the process of their evolution, the clusters around the voids, they give their AGN feedback often into voids. And that's why in simulations, it's seen that the hot gas within voids slowly increases. And one of the things that we wanted to do in our study was to see what is the contribution from the galaxies within voids themselves to the hot gas. So to do this, we first looked at the nearby void galaxies, which have been studied in detail. And one of the best voids to look at is the Bootes void, because it's nearby, well studied, and the galaxies are very typical of void galaxies. Now, when you have voids, the smaller voids are composed mainly of dwarf irregulars and low luminosity galaxies. But when you get to the larger voids, like the Bootes void, you get these star-forming galaxies, which I've shown here. And the galaxies have this distinctive structure that they are mainly star-forming. They are mainly blue. And this is very important because several decades ago, when void galaxies started being detected, people predicted that they would be LSB, low surface brightness galaxies. But that's not true. They are mostly slow evolving galaxies, and they lie in the blue part of the color magnitude diagram. And this is a very good example of a void galaxy in the local void, NGC 6946, which is, as you can see, very full of star formation. One thing which I didn't show here is that it has a huge H1 disk. And even at the edges of that H1 disk, you see star formation, very localized regions. And that is a hint at what the star formation properties in these galaxies is like. It's not just concentrated in the center, as in these galaxies, but it can also be at the boundaries of the galaxies, triggered by gas accretion onto the void galaxies. This gas accretion is happening, and as you can see here, like a triplet of galaxies, the gas accretion happens because of the filaments within the voids, the filaments of the cosmic web. And cold gas accretion can trigger star formation in these galaxies. And when you actually look at the samples of void galaxies, you'll find that a very large fraction are in the form of binaries or triplets. So there are definitely indications that there is a kind of a substructure which can be traced by galaxy filaments within voids. And as I mentioned, there is a lot of significant star formation which can be triggered by gas accretion onto these galaxies. And this is NGC 6946, which I just showed you. And again, here you see very clear indications of abnormal H1 velocity, which indicates gas which is slowly accreting onto the galaxies. Now, why study void galaxies? I showed this slide because I remember when I went to a large-scale structure meeting, some of the people said, you know, why study these galaxies? They're just small little things, blue things, and we know all about them. They're very good examples of slowly evolving galaxies. But void galaxies not only allows us to trace the growth of structure in the emptiest part of the universe, it also allows us to trace the evolution of isolated galaxies. And that's what I'm going to concentrate on, the evolution of the gas around these galaxies. So the first slide I'm going to show you about is the first day talk that Tuhin gave. What we have done is we have stacked the SZ maps, thermal SZ maps of void galaxies. We've avoided the directions of the clusters, and we were actually able to detect a 3 sigma signal for the TSZ effect using void galaxies. Now, generally, TSZ signal is detected from clusters or from binary galaxies, and you can actually detect the filament between them, which is the cosmic web. And it's also detected around quasars, and that is the CGM, which Biman just talked about. But all those cases were triggered by one thing, and that's AGN feedback. You must have a massive, supermassive black hole accreting mass, throwing out gas, making a CGM. But stellar feedback is also a very important part of feedback in our local universe, and that is what void galaxies allows us to probe. And so this is M82, and it's got beautiful winds here, and this is a clear example of stellar feedback. And this is the signal that we detected using void galaxies from a catalog, Panetal catalog, using about 20,000 void galaxies. So the question we asked ourselves is that do void galaxies contribute to the warm, hot gas expected in voids, which people have seen in simulations, illustrious simulations. So to do this, we looked at the nearby Bootes void, which has now become my most favorite void, because it has just so many AGN. It has 5 AGN actually. 4 of them show radio emission. And so we targeted radio observation as these galaxies to explore the diffuse emission around these galaxies, and not just to probe the stellar feedback on the AGN feedback. The other objective was to see that are these regions where we can detect low frequency emission, because we know that one of the aims of SKA is to detect at very low frequencies, 150 megahertz, the cosmic web, and that's at the scale of microjanskis. Now, to do that, voids are one of the best places because voids are very empty, there's no confusion. When you go near a cluster, there are just so many filaments, it's very difficult. So close to the edges of voids, looking for the cosmic web in those regions is an ideal place. So keeping this in mind, and because we wanted to see radio emission from these galaxies, unique galaxies, we did these observations. And we did it with the GMRT before its upgrade, but we still think our observations were quite good. We are continuing with more isolated galaxies. We did 240 megahertz and 610 megahertz. Void galaxies have never been observed at such low frequencies before. We targeted the Bootes void galaxies, as I just mentioned, and that's because the Bootes void is one of the largest low redshift voids in our universe. And because it's so large and possibly had many subvoid mergers, it's got more bright galaxies which have AGN, and we targeted only those galaxies. Now, since I'm a little short of time, I'll just flip through the results. This is one of the galaxies. The galaxy is shown here in near infrared, and this is the emission at 240, 610. As you can see, it's quite compact, the emission from these galaxies. The 3 of the galaxies, we got fairly compact emission. This one is a little more extended. This emission is coming from the AGN. So it's showing how the AGN feedback is pushing gas, as Biman talked about earlier, pushing gas into the circumgalactic medium. And their circumgalactic medium is a little smaller because they are slowly evolving galaxies. So for the system for which we obtained really nice results was this system, CG 692, 693. And this is an interacting pair. This galaxy is a Cepheid-1. This galaxy is starburst. And what we find is beautiful low frequency emission around the starbursting galaxy. And when we did the spectral index, we got a fairly steep, for CG 692, we got a fairly steep spectral index, which indicates it's probably due to star formation. And we also determined the magnetic field. The magnetic field is important because in the void regions there is no really detection of the magnetic field. Now we also looked at X-ray emission because X-ray traces the hot circumgalactic medium. And what we found is that this pair, interacting pair, the one which had a huge starburst diffuse radio halo, had nothing in X-ray. However, the Cepheid-1 galaxy had a beautiful X-ray emitting circumgalactic medium around it. And if you look at the figure here, you can see a small alignment. It's tidally interacting with the other galaxy, so there's a small alignment here, and a small amount of filamentary structure. And here I have just shown it in more detail. We also looked up the archive and we found that there are other cases where you have X-ray emission around these galaxies. These are good candidates in which to study the evolution of the CGM because they're just so isolated. They are not affected by other nearby galaxies. So I'll stop here. I have another minute. Okay, so I'll stop here, but since I have time, maybe I'll go over the results again. So we've been studying void galaxies. Our main aim is to study the diffuse emission in these galaxies, and we looked at it in using Planck data. We looked at it in low frequency radio, and we've also detected it in X-ray. What we find is that if we stack something like 20,000 void galaxies, we are able to detect a weak signal of the TSZ effect, which is due to the stellar feedback from these galaxies. This is important because I think in future surveys, when the resolution will become even better, we'll be able to detect this in greater detail. And void galaxies gives you an opportunity to study all these features in total isolation. When we looked at the Boötes void galaxies, we found that they do have low frequency emission. Some of them which are interacting will probably have more emission, and they may be even having filaments, which we will be able to detect in future surveys. And voids present a very good environment to do this detection experiment because they just are so empty. And so the signal to noise of any filaments that you will see will avoid all confusion. And we've also found that diffuse emission in X-rays exists around these galaxies. This is not the first, ours is not the first detection. It's been detected in BROSAT many years ago. But we found that the Chandra archival image of this galaxy showed a beautiful evolving circumgalactic medium, which we will be hoping to study in more detail later. So I'll stop now.
Thank you.
Thank you, very nice talk. Regarding your first point there, how can you be sure what you detected is not infrared emission from, because the Planck Y maps, they are known to have some residual contamination from star-forming galaxies, which pretty much is what is dominating your sample.
Yeah, they are star-forming galaxies. We've avoided the directions of the clusters. So the galaxies seem to be isolated, but I'm not sure about what you mean by contamination, because this is...
Yeah, the Compton map is not purely SC. It's SC plus CIV, some residual CIV, and some residual signal from especially bright infrared galaxies. Okay. So it's not completely ESC. So when you stack especially spiral galaxies, you're going to be more affected by this effect than when you stack clusters, for instance, where you have a mix of galaxies.
Is this dust that you're talking about?
Yes.
Oh, okay, yeah, we have used dust masks. Tuhin talked about it in his talk. The Milka and another one. So we have used those maps, the masks.
Well, let me tell you, that is not perfect, that.
Okay.
They don't remove everything perfectly, so.
Okay, maybe I'll talk.
Other questions? So I may be confused, but you said from the spectral index of the radio detections in bodies, you think they are star formation caused?
So if they were totally AGN dominated, then we would get something close to zero. The spectral index would be closer to zero.
Right.
So there is a mixture of both star formation and AGN in the emission that we see.
Okay, and
So
these are relatively isolated, even within the
They're
void,
totally
right?
isolated, yes.
So what do you think would be the cause of the AGN activity? Just secular or?
Yeah, secular. They are evolving. They're evolving within the web inside the voids. It's a slow growth, but they are evolving. They do have bulges, so they are AGN consistent with the bulge masses.
Okay. Okay, so if there is no more questions, then let's thank the speaker.